Hi, welcome to a lecture on model selection using AIC. AIC is a pretty familiar acronym to lots of ecologists now. It stands for the AICs Information Criterion, named for the man who invented it, and actually he worked from some existing theory as well, Dr. Aiki. He works in Japan. He did a lot of this work in the early 70s, but I'll walk through that in just a moment. It took a while before people caught on to it. It was known within his world, but not outside of that. So ecologists didn't really know about it until doctors Anderson and Burnham pulled it together and explained it to people and helped us understand why it was relevant to us. So I want to walk through that very brief history here so that you understand how model selection, yuck yuck, is an important part of what we do now. So you'll see why it's only relatively recently become such a major part of how we do our science. So to understand why it's important, I want to remind you what null hypothesis testing does and doesn't, and then why AIC approaches are the antidote, or at least a counter approach to null hypothesis testing. That sets up the idea that we'll be comparing multiple alternative models. Hopefully you remember why that was important, going way back to some ideas from the late 1800s. And then all I want to do is introduce to you the basics of AIC and a version of AIC which we really use actually far more often, called the AICC. It's the corrected version of AIC. And when we report AICs, it's also very important to report something called the delta values and the weights, and I'll walk through those as well and use that with a brief example. So hopefully you'll understand what these are used for, why we use them, and hopefully you'll understand why it's going to be a pretty big deal in how you do your work as well. Okay, so let's walk through a history very quickly. Aiki first introduced some of these ideas in a symposium proceedings published in 1973. As you might guess from the title of the book, etc., it wasn't probably widely known outside of the set of people who work in information theory and might have been involved in that in the 70s. Now remember, this is pre-internet, so there weren't very many sources to tap into that. You would have had to have been at a fairly substantial library to have access to this and been involved in information theory to be able to even aware that it existed. So information theory is this great big body of research, including Shannon entropy. You might have heard of Shannon diversities. It's really related to bits and bytes, etc., binary type of data. The idea is that we have information that is less likely because the less likely an event, the information that comes with that event actually is more valuable. Okay, so an entropy, as you might think of it as physical entropy or thermodynamic type entropy, is zero when you have only one outcome that can occur. There's really nothing left to be understood, in other words. Okay, so this is all based on probabilities of events and the idea that information is related to those probabilities, and entropy is an expression of the idea that information coming from a rare event. So we're really dealing with probabilities and likelihoods is really the underlying theories of all this. It's pretty complicated, and I'm not going to pretend I have a full grasp on all of this, but it's surprisingly at the basis of a fair amount of our ecology now, not only because of the AIC scores, but also related to Shannon entropies, which have been a pretty big deal in diversity measurements. Okay, so as you might guess from Burnham and Anderson finally writing a book about this in 1998, it lay fallow for 25 years as far as ecologists were aware. Okay, so there's this slow evolution of this, or awareness of this moving into ecological worlds. So they wrote their book in 1998, and you notice that in all of this time, even since 1998, that book itself has only been cited by 80 different papers. Notice that then a couple of other papers that followed in 2000 and 2002 by the same authors, Anderson and Burnham, also including Thompson, now started picking up a lot more notice. This paper especially, the one in the Journal of Wildlife Management 2000, caught a lot of people's attention because they explicitly came right out and attacked what was, and maybe in some people's minds still is, a major precept of how we do science, null hypothesis testing. They explained very clearly, it's a nicely written paper, on the problems with null hypothesis testing and the fact that we're still doing it so often and that we should be moving on to a new approach based on the AICs. They followed that up a couple years later because now obviously people were starting to think about it, and they said there are some problems you have to watch out for if you use these information theory kinds of methods. There's certain recommended protocols, procedures that people would have noticed if they'd actually noticed this book that had come out. And so then fairly soon right after that, they came out with their second edition of their book, and boom, people since then have really caught on. Largely because this paper caught people's attention, and now 25,000 or so times later, this book has been cited. That is remarkable in terms of the rapid expansion of this in people's minds and how firmly it has taken hold. Okay? As evidence of how rapidly this has taken over, I used the Web of Science through our library, just simply searching for, in the Ecology section, topics of archaic information or the abbreviation AIC to represent AIC uses. That's just keywords, and I think it appears in the title of the abstract. And I compared that to null hypothesis, appearing similarly in papers within the Web of Science Ecology section. Now this is obviously a subsample of all the papers who might be using one or the other. It's just having been listed in the text of titles, abstracts, and keywords. So you notice, however, with this sample, it sure looks like null hypothesis peaked, let's say, in the early 2000s and is starting to come back down, whereas AICs have crossed over in about 2004 and have now surpassed that pretty dramatically and look like they will continue to keep going at least somewhat up. Now, the point is that AICs have transcended the use of null models in ecology. Okay? So we should be pretty aware and pretty comfortable with how to use these things. So let's walk through that difference between null hypothesis testing and AICs. A null hypothesis test, as you will remember, is simply saying that a mean is 0, or that a difference between data sets might be 0. That, in other words, there's really no pattern to report, nothing of great interest. Complaints against null hypothesis tests have been that we are confusing a scientific hypothesis with a statistical hypothesis. A null hypothesis is a statistical test. It is a tool that we use. It is not the thing that drew us to do science in the first place. So, in fact, the null might be biologically trivial. If you found that there was no difference between two treatment groups, that tells you that there might not be some sort of effect due to the treatment, but doesn't really tell you anything about the biology of the system necessarily. You might be thinking about far more substantive matters that set you out to do this experiment in the first place. The single hypothesis focus that comes from a null hypothesis test of two variables, etc., two factors, that negates the multi-hypothesis science with a capital S that was espoused by Chamberlain and Platt. You remember those papers that we read early in the semester. We'd forgotten, essentially, how to do multiple models by focusing on null hypothesis testing. That occurred as a result of having confused scientific hypotheses with statistical hypotheses. And by doing a null hypothesis test, we tend to focus on the p-value. Did you get a significant difference or not? Was it less than 0.05? Focusing on that forgets that that cutoff is just a matter of custom. We don't necessarily have a reason to expect 0.05 to be something especially notable. And that also then tends to neglect the reporting of effect sizes, the coefficients in a model, and model strength. Those two things tell us a lot about the results, and people have too often reported just p-values and not reported these other important values that help explain what happened in the set of results. So the null hypothesis tests have, because of time and practice, actually been somewhat of a confusing issue because we've neglected how to fully report our results, and we've been so focused on p-values that we've forgotten that that's not really a scientific hypothesis. So the antidote, remember Chamberlain and Platt. Think first is essentially what they argued. And think carefully about your alternative hypotheses. Design a study to test those alternatives. Be careful to think about them fully and imagine all the possibilities. Then be able to collect the data to evaluate those possibilities. Evaluate that list of alternatives to find out which model is least bad, because remember, all models are wrong, but some are informative. That's an old truism. So you're just essentially trying to identify which model is the least bad. You could say best if you wish to, though people hesitate to do that often. You might call it the most plausible. You might call it the most efficient model. In other words, it represents the most information for the least amount of variables involved. It might be the most likely to be truthful. Those models then, those model comparisons, are helping you show which model seems to be the most reliably approximating the truth of your data set. Okay? An important detail here is that if you thought first, developed alternative hypotheses, compared them, and identified your quote best model, it really is only that model among the ones in your list. If you had neglected to fully list all possible alternative hypotheses, maybe forgotten a very important one, it's not on your list, then your answer will perhaps have neglected the important hypothesis that was omitted from your list, right? So it's important to have tried to think well, think early, think often, etc. about alternative hypotheses. That's just reiterating what Anderson and Burnham have reminded us regularly in their papers, but it comes back to what the man with the grand goatee here, Chamberlain, had been telling us to do from the very beginning. Think carefully about those multiple working hypotheses, develop those, and develop tests for those. Okay? So he's really, I guess, without having known it, the progenitor or the founder of this AIC approach, in that his ideas were the template which we've finally returned to by using these clever statistical tricks. Okay. So if we are comparing multiple alternative models, it would be useful to understand when might you do that versus when might you think about analyses of variance or regressions, the way we've been analyzing data already so far. Okay. So the classical analyses of ANOVAs and regressions might be compared to those of multiple models. And you know what these are doing already. You might run a full factorial model, for instance, in ANOVAs. And what you get is the answer. You did the ANOVA, you find out there's significant interactions or not. Some of the terms might not be significant. And Crawley, the man who's had a lot to do with helping us understand how to work with R, big thick book I have on my desk here, really espouses actively that then you should simplify down to the most parsimonious model. If you had terms that were not significant, you can exclude those, for example, interaction terms, leaving individual terms in the model to explain your data most fully. Okay, so that ANOVA regression kind of approach with this most recent parsimonious approach has been fairly classic. The multiple models approach would be not necessarily just running this one full model, but you might run each model and you might compare then those alternative models, factor A, factor B, and the factor A times B, etc. kind of idea in factorials, and then compare those to see which one is most likely true. In an ideal world, we would say that these two outcomes would match. There are some conditions where they may not, if you get into some difficulties and more complicated analyses. But so what we're trying to get to here is when might ANOVAs be most appropriate and when might you think about an AIC as being more appropriate. Ideally, they would be telling you the same thing, but a lot of people have been working through this and thinking about it, and what I've been gleaning is that general recommendations are that an ANOVA works pretty well if you have a planned, controlled experiment, one where you've randomized your experimental units among the treatments, you have replicated those treatments so you have multiple units for each treatment, and you have relatively few treatments, so it's a fairly straightforward, simple experiment. Now, if you've done all that and you figure out you have some significant difference, that's fine, but to get past some of the criticisms of people who've been doing ANOVAs for a long time and focusing on p-values, we should remember to report the coefficients from our output models, right? We should be able to say what the term is for treatment A, the term is for treatment B, etc. because that is important to understand what the treatment effects were. Not just the p-value, but those coefficients and their confidence intervals. Those are the effects, essentially, and you can tell a lot about how variable it is and whether it's significant, etc., from the confidence intervals. Secondly, also report the R squared, the strength of the model that tells us a lot about how well those data represent the total set of variation. Okay, so if that's when to run an ANOVA, when might you plan to use and rely upon more AICs? Well, and I'm going to keep emphasizing AICC here, you'll see why in just a moment. You should focus on those when you have more complicated experiments instead of relatively simple ones. Mixed effect models, nested designs, more complicated analyses where you need to try to account for multiple kinds of sets of information. You should especially think about using AICs when you want to evaluate multiple regression models. Those are very appropriate, and of course, as I hope you're understanding soon, if not already, that they're very related to ANOVAs. Many times we're collecting data, observational data, or we're taking measurements along a gradient and looking for a response. Mensurative models, in other words, as we've heard before earlier in the semester. If we're doing those kinds of studies as opposed to relatively simple experiments, then AICs are very much the appropriate way to compare those models. And even with AICs, we should remember to report the coefficients and the confidence intervals and the R-squareds of our model that we decide is, quote, best. Okay, so if we can remember that ANOVAs are usually going to be quite reliable and don't have to be replaced by AIC approaches when they're fairly simple and well-designed experiments, but AICs are appropriate when we deal with much more complicated analyses. It also might be useful to say, well, how often do we compute and compare treatments in relatively simple experiments? That would be great, but it turns out in reality, a lot of our experiments tend to be these messier mixed effects, nested designs, and a lot of times we're computing regression models across lots of observations without even having conducted an experiment with treatment units, etc. So you're going to see that AICs are pretty commonly used in the literature in our discipline, and you'll probably end up using them yourself in many cases in your career. Okay, let's walk through the basics of what an AIC is and its perhaps more common AICC values. Then we'll get around to explaining what deltas and weights are as well. So what's an AIC? The AICs information criterion is simply N, which is the sample size, how many samples you have, how many units you are in your analyses, times the log base E, the natural log, in other words, of the variance divided by N. Okay, and that variance divided by N is the residual sum of squares. Let me say that again. The residual sum of squares divided by N is this sigma, the estimated sigma squared. Okay. So the residual sum of squares divided by N is the same as sigma squared. And we add to that 2 times the number of parameters in the model. So if I have a model that is y equals a plus bx, that's a, b, and we have to remember that there's an error term. So I actually have 3 parameters in the model of y equals a plus bx, right? Because there's an error term as well. All right, so 2 times the k times plus the n, the sample size, times the natural log of your residual sum of squares divided by n. Well, we can get the residual sum of squares from every regression from every ANOVA. We can calculate the sample size or look it up. We should know it already real easily. And the number of parameters in the model is easy to calculate. So you can see you can do this with a handheld calculator, a spreadsheet. I've done these many times just using a spreadsheet calculation based on analyses of variance residual sum of squares that I can lift out of a table, for example. Okay. Now, how's the AICC different? I'm going to keep coming back to AICC. You'll see why in just a moment. It's the same basic equation as above, but we add on this extra term. And all that this does is it adjusts ultimately for n minus this k minus 1 bit down here. N being the denominator down here says that we're basically adjusting for the size of the study. Okay. So it's k relative to n. The k is the number of parameters, and n is the size of the study. So if we are thinking about what AICC does, AIC is not adjusted for sample size, where AICC is the corrected version. That's what the lowercase c stands for. It's corrected for sample size because this whole term here divided by this term is including sample size down here. Okay, so AICC is really best when you have a large K relative to N. Now, what does that mean? Well, it means essentially that there's a rule here. Just use AICC. For almost everything we do, well, I'm going to just say for everything we do, you should just plan on using AICC. And it's very easy to report it. We'll walk through in lab, etc., can report this very simply. All right, AICC is best almost always. I'm going to say always because it up until you get an n relative to k approaching 40. So that means for every parameter in your model, you have to have 40 replicates, sample size of n, right? So I would need 40 sample units, experimental units, for every parameter before AICC starts to be only comparable to AIC. So in other words, once you get to this 40 or so of n relative to every k, it converges to AIC anyway, which means that for the times when you have less than 40 replicates for every factor in your model, and that's a lot of data, then you're going to use AICC. And when you get up to that number, you might as well just continue to use AICC because it becomes the same value as the plain AIC. Okay? So that's why I say this rule should be really simple. Just use AICC and you're good to go. Okay? So remember, we can compute AICC with this simple equation, and R will calculate this easily enough for us. But even if you had to, you can do this real easy with a calculator or a spreadsheet. Okay? So you get your n, the number of samples. You get your k from the number of model parameters. Don't forget the error term. That's something I had to learn the hard way. And then you record your residual sum of squares divided by n to get your sigma squared, and you solve the equation. Okay? Or otherwise, R will do it for you in a lot of different outputs. Okay, so we know what AICC is and how to calculate it. There are these two other pieces of this that we need to understand, the deltas and the weights. And I put Anderson and Burnham's pictures back up here again because they really explain these nicely in some of the papers that we have for the course, and also in their book that is a very useful resource if you need to work with these things. So when you're reporting these AICC results, you report the difference between the lowest AICC and the next one. Now, the reason it's the lowest is because remember, this is a measure of entropy, and the lower model will be the best, where you want to have the least entropy essentially. So we're looking for the lowest AICC to be our best model. So the difference between your quote best model and the next one is the difference, or delta. Delta is common for the difference or change in something in a lot of symbols. So these differences help tell us the relative values that we have in the AICC. The larger the difference, or delta, the less plausible the model. And that means the first one would be a delta of, a delta of 0. There's no difference if you're looking at your first model. The delta is attached to the second variable, right? The second model, I should say. Now, the other important thing is to report the weight of each of these AICC values. And that's also really easy, and again, R can spit it out for you in a table, which we'll walk through again in the lab. And that's real easy. Exponent, or e to the minus half of delta, divided by the sum of all those minus exponents of minus halves. So you're just basically looking at this likelihood. This e to the minus half of delta is the likelihood, and you're looking at that relative to the sum of all of those. So w sub I then would sum to 1 if you add up all these things, and you're seeing how much the likelihood is out of the total likelihood of all models. So in other words, it's the probability that a model is the best or most likely model among those listed. Okay? So the weight really turns out to be the factor that is going to be most often the one that you would use to say, and this is my best model. It is backed up by the deltas and the raw AICs. So often people ask you to report a table that shows the AICC values, the deltas, and the weights, but the weight is really the one that's going to be the deciding factor on what turns out to be the best model. Perhaps this example can help. This is from some data I'm actually just recently submitted in a journal paper. And so I have alternative models. I'm simply comparing a quadratic to a linear model. So I have a plus b plus a quadratic function here in this equation compared to a simple linear equation. The AICs for the data come out this way. And you look at that and you say, okay, well, this one's lower, but they both look like pretty large numbers. The delta helps make that more clear. And you see there's a pretty decent sized delta here. And then the W sub i's, bam, this is really showing that the first model, the quadratic model, is absolutely the best model. Remember, all the W sub i's will sum to 1, and this is really no different from 1 because all the other ones, even if I had a longer list here, in this case only the second one, is trivial. It's far, far less than, this is actually then, 0.9999 something. So the point is that this one is really not a plausible model at all, the linear model. The easily most plausible model here would be this quadratic function. Now, I also, in this set of results, reported the coefficients, whether they are significantly different from 0, and their confidence intervals. Those are the A's, the B's, and the C's, okay? And the adjusted R-squared for these models to show that this represents slightly more variation than that one. Now what's interesting is that in the past, before we used AICs, you might have only looked at the R-squareds. That's all we had to deal with. And you might have concluded that, well, they're not that bad. The linear is not that bad relative to the quadratic. It's not wildly different in the R-squareds. What this is telling us is that this is far more likely to be the true pattern in the data than this second one, despite having an extra term up here. Because remember what the AIC is doing, you're discounting the model for extra terms that are added on there, that K term. So we're actually seeing that the greater, more complexity in this model is okay because it's still providing far more information and able to far more confidently be expressed as the most likely model, most likely to be true. Okay. Now these variables here, the A, B, and C, etc., are not used in the inference of which one is the most correct model of the list here. They're only just help report what A, B, and C and the significances might be. Now, I should say Burnham and Anderson are quite explicit, and emphatic even, that these significance values should not be part of the inference. They're not here. I'm just reporting them and showing what those coefficients might be in their confidence intervals, the same way that these are only for information purposes as well. All of the decision on what was the most plausible model is all based up here in this table. Okay, so all of this is just accessory information for the inference, but it will be useful if somebody else wants to know how to compute what the equation look like, right? Okay, so hopefully that helps you see one example. Now, you might easily imagine that these two W sub i's might not be as wildly different in another case. Perhaps this was a 0.6 and the next one below here is a 0.4. Well, you might still be able to report that one is a decent model relative to the second one, but you might be less confident in saying, I can stick with one. You might have to say, well, both models are pretty close to each other. And that's the other valuable thing that comes from AIC. You don't just stick with one model, as you might have if you're only computing one. You can say, well, they're not too far different if the weights are not too wildly different. Okay, so you get to evaluate multiple models. You also get to be able to say, well, there's not a huge difference between one and another. These are two comparable models if the weights turn out to be fairly similar. Does that make sense? Hope so. All right, so when do we use ANOVAs and when do we use AICCs? Well, since about 2004, AICCs are far more commonly used, but it doesn't mean we throw out the baby with the bathwater. ANOVAs are still fine. For relatively simple experiments, we have randomized treatments and they're replicated and it's a fairly simple experiment, less than 3 treatments for instance, but we should be reporting these coefficients. We should not forget that those are important, and we should also include the R-squared so we know what kind of strength there was to the model. AICCs, though, are far more appropriate when we're dealing with more complicated models. They're very appropriate for comparing alternative regression models and observational types of studies where we can also report the coefficients, confidence intervals, and R-squareds. So I think it's going to be important, if you want to really understand this, to read a little bit further. I've included these first two citations in our readings for this course. They're both very cogent and easy to read papers. The ones that really got the ball rolling here. The null hypothesis testing, problems, prevalence, and an alternative lays out the great argument, and in fact I've used that to do all these calculations by hand in a spreadsheet. It's really not hard to do. That paper is very useful for understanding what AIC is and why it's useful. And then after people got using it, they started explaining to people how to report it correctly, how not to do things the wrong way. And if you found that you wished for more information, despite having those two papers, there is this book available, but as you know, some of the books from Springer and other publishers are not cheap. So I would recommend try these first two papers first, and that hopefully they get you a long way towards doing AICs. We'll be doing AICs in lab. We're going to be messing with them a lot of the rest of the semester, so you'll be very comfortable with them by the time the semester is over. All right, I think that should do it, and I'll see you in lab. Bye.